Hello and welcome to the 30th lecture. So today we're going to be talking about the fundamental theorem of calculus. And we start this with introducing this function that initially seems a bit strange, but we will talk about it for a bit and hopefully it'll seem more natural as we go along. So given continuous function f on a to b, we define g of x to be the integral from a to x f of t dt. Okay, so as always, the picture clarifies what this is actually doing. I call this the increasing area function. Okay, so if we have a function f, let's say it does something like this. This is f. Then what does the increasing area function do? So if we take x to be here, then this is the signed area all the way from a up to x, like this. Yeah? And as you can see, as we move x between a and b, this thing is some quantity. It's a well-defined quantity, right? If x is somewhere between a and this part, it's a positive quantity, right? And it keeps increasing as we go further and further. And as we cross this part here, then we have more and more negative area, and then this quantity is going to be decreasing. Yeah. So you probably haven't seen functions defined out of integrals before, and this might seem like a strange expression, but the expression is just in the language of maths, this picture. And this picture, I hope, is fairly straightforward to see. Yeah. Okay, so this is the increasing area function. And the big reveal is that this thing is an antiderivative of f. And why that's the case is very straightforward from pictures, and I'll show them to you shortly. But first we have to get comfortable with this thing. We have to feel okay about this. So we're going to do some exercise to kind of warm us up about this function g. So this is the first example. Example 1, we're going to take this function f with the graph given as follows. It looks like this. So we don't need this. So this is 1, 2, 3, 4, and then 5. So here is 2. So initially f goes up like this, and then from 1 to 2 it goes along. And then from 2 to 3, it doesn't go down diagonally. It's got this kind of a curve like this. It's a bit more of a curve. And then from 3 to 4, it's kind of a mirror image of that curve like this. And then 4 to 5 like this. Okay? That is our function. Okay? And define g of x to be the integral from 0, so this guy starts from 0, to x of f of t dt. So since we use x in the definition of g, we're not integrating with respect to x, we have to introduce a new variable, and that's going to be t, right? So this is our function. Then find g1, g2, g3, g4, g5. Okay, solution. Okay, so we're gonna sketch them in one by one, right? So G1 is this quantity right here, yeah? And what's this? This is a triangle whose base is 1, whose height is 2. So we have that G of 1 is just equal to 1, right? So you can also just see from this that this triangle is exactly half of this rectangle, whose base is 1, whose height is 2. That rectangle has area 2, so half of that is 1. So G of 1 is 1. Yeah? Now G of 2. Okay, let's sketch it in. G of 2 is everything from 0 to 2, right? So it's all this stuff. Yeah? And what's this? This stuff here is area 1, and this next part has got area 2, right? Because it's got base 1, height 2. So the total of those things together are just 3. Right? So G of 2 is 3. Okay, G of 3. Then it's also this stuff. Yeah? So G of 3, it will be 3 plus this thing. Now this thing isn't quite going along like a diagonal. It's got this kind of curve to it, so it's got a bit more area. So it's going to have more area than just 1. And let's say it's got area 1.3, this stuff here, between above 2 to 3. Huh? So we have everything, all the area from 0 to 2 plus this extra stuff, which has area 1.3. So this will be 4.3. Yeah? And then G of 4. Now I'm going to change color because now we're having some negative area, right? This stuff is negative area. It's underneath the x-axis. And since this is the mirror image of this thing, this stuff will have negative area minus 1.3, right? So we have all of this stuff, which has got area 4.3 and then minus 1.3. Now G of 4 will just be 3. Yeah? And finally, G of 5. This stuff here, this negative area stuff here, again, it's the mirror image of this stuff, so it's minus 1.3, so we're going to go from 3 down to 1.7. And that's it, right? So we can understand G. G isn't particularly hard to get a grip on, right? Okay, cool. So that's what function G is. Now, we're in a position to state fundamental theorem, calculus part 1. Okay, suppose f is continuous on the interval a to b, and let, just as before, g of x be defined to be the integral from a to x of f of t dt. Yeah? Then g is an antiderivative. Of f, i.e. g prime is equal to f. G prime of x is equal to f of x for any x in this interval. Okay, so this is actually the heart of the fundamental theorem of calculus, and I'm wondering if I have enough space. Okay, well, let's see how this goes. So let us draw a picture. So here we have our x-axis right here. Let's say this is A, and over here is B. Okay? And let's create our function, say this is f. Yeah? And let's take x to be here. This is x. Yeah? And then let's take x plus h, which is here, right? So we're just moving along by h. We have x plus h right here. Yeah? And then let's consider this quantity g of x plus h minus g of x. Well, what is g of x plus h? That is all of this stuff, right? That is all the area underneath the graph from A up to x plus h. So let's color that in red. And what is g of x? G of x is all the stuff underneath the graph from A up to x. So let's color that in blue. So, g of x plus h minus g of x is just all the stuff in red minus all the stuff in blue, which is just this strip right here. Yeah? So this strip has area g of x plus h minus g of x, right? Yeah? But if we try and estimate the area of this strip just from this picture alone, we have that the base right here is got width h, right? So it's this thing right here is just from x to x plus h. So this has just got width h. Right? Yeah. And then how high is this strip? Well, if we go along like this, remember this thing is the graph of f, right? So this is f right here. So the height of this guy, of this strip, well, it's not completely flat here because the function is moving a little bit, but it's a continuous function, so it's not actually moving that much as it goes from x to x plus h, because h is very small. So this height is pretty much just f of x, right? Right? So that means that this area right here is also well approximated by just the width of the base of the strip times the height, or the approximate height of the strip. Yeah? So this thing is approximately equal to h times f of x. And if you want to be really precise, it's not quite this because there's some sort of error here. So if I had like a steeper kind of slope right here, imagine if I had a slope sort of like this, yeah, then I would not be counting this part right here, right? That would give me this little error, yeah? But this little error is really small compared to the actual area of the strip, right? So this error right here size is about h times something, at most some constant times h. So this error is something like h squared, yeah? At most some constant times h squared. So it is pretty negligible compared to the actual width of the strip. So if I was going to be more accurate, I'd put h times f of x and then plus or minus something of order h squared like this. Yeah? But this thing is going to be not important because I'm just going to divide by h. So if I do that, then I just have f of x and then something which is of order h itself, right? And then I'm going to take the limit. So g prime of x, which is equal to the limit as h goes to 0 g of x plus h minus g of x over h is just going to be equal to f of x, because as h goes to 0, this thing's going to 0, and we just see it. Yeah? So what we've just shown is that g is indeed an antiderivative of our function f. And it's just this picture. It's nothing more than this picture. Yeah? So we now have an explicit antiderivative for our function, and that allows us to do some easy calculation. So let's squeeze in a simple example right here. So example. Suppose we have g of x is equal to integral from 0 to x of the square root of 1 plus t squared dt. And we want to differentiate this. Is g prime of x. Well, this is just a simple application of this actual theorem. We just f is equal to this function, right? So f of x is equal to the square root of 1 plus x squared, and we're exactly in the territory of this theorem. Yeah? So by fundamental theorem of calculus part 1, and I'm running out of space. G prime of x is just equal to f of x, which is just equal to this thing. And that's it. If you're in any doubt about this, if you're feeling uncomfortable about just applying a theorem, just draw this picture for this particular example of a function, right? So let's squeeze it up here. The method of why the theorem is true is much more important than the statement of the theorem. If you're happy with the method, then you can just apply the method to the actual thing that you're looking at. So what does this thing look like? Well, it's 1 at 0. It's kind of curling up like this. If we take the derivative, so this is the function, square root of 1 plus x squared. If we take the derivative, right? So we do the same thing. This is x. This is x plus h, right? Yeah? So then if we take this quotient g of x plus h minus g of x over h, yeah, it is just the area of the strip divided by h, which is more or less the value of square root of 1 plus x squared, right? And it's more and more this value as h goes down to 0. So this is not a hard thing, right? This theorem is not a hard theorem. It's from this picture, and applying it isn't hard. You just might feel less comfortable with it because you're not used to seeing, again, functions defined in terms of integrals. But we can get used to it. All right, I'm going to erase the board. We'll do another example, and then we'll see why this has so much impact. Okay, let's do this example. All right, so the fundamental theorem of calculus part 1 is such a basic thing, such an important thing for you to understand. We need to examine it, but it's hard to create questions to examine it because if we ask something like the example I just did, then it's just trivial, right? It's just too easy to answer. So one of the few ways we can create a non-trivial exercise is to set something up like this. And since we have to examine it, and since it's hard to create questions, and there's only a few variations we can actually do, there's a very high likelihood that you'll see something extremely like this. So if you look back at the past exams and you look at the past exam, the question that is testing this will probably have some format like this, right? So it is well worth your while being able to answer this question. And this question might look like it's a very different question, but it's actually not. So solution. All right, so first thing to note, it looks a bit like the kind of thing we were just doing, except it's going from 0 to x to the 4. So if we define g of x to be the integral from 0 to x of sec of t dt, then that guy we're happy with, because that guy we do know what the derivative is. The fundamental theorem of calculus part 1, it is just sec of x, right? So if we had that guy, we were fine, but the problem is that we have this guy, right? But if you think about it for a little bit, what you should notice is that this guy here is equal to g of x to the power 4. Yeah? It's g of x to the power 4, right? Just we stick in x to the power 4 into this thing, and there we go. Yeah? So then, if we do to differentiate this thing, because our problem is now to differentiate x to the power 4, g of x to the power 4, then we're happy because this is just going to be applying the chain rule, so it's just g prime. Yeah? Just the chain rule. And this thing we actually know how to differentiate. We know the derivative is just equal to sec x, right? So g prime applied to this number x to the 4 is just sec x to the 4. So this is just sec x to the 4, 4x to the 3, and that's it. That's the answer. Huh? So this thing, so star is equal to this. So it isn't particularly hard if you have the right trick. If you don't remember this or you can't think of it, then it's really hard. And the key is just we're going to rewrite this thing we don't understand as a composition of two functions, each one of which has a derivative that we do understand. We certainly understand the derivative of x to the 4. We certainly understand the derivative of g, and by the chain rule, that's all we know to understand this derivative of this composed function. So that is a question you'll face with high likelihood. Please practice these kind of questions. Be ready for them. If you have this trick, it is not hard. If you don't have it, if you forget it, then you're really stuck. So yeah. With probability 80% or more, you'll see something like this, at least in one of the following exams. Because, again, we have to examine this, and it's hard for us to come up with non-trivial questions. Okay, so that's the fundamental theorem of calculus part 1. Now part 2. So, first, a true fact. Suppose g, f are antiderivatives let's just call them anti-Ds of function little f. Yeah? Then what does that mean? That exactly means that g prime equals little f and f prime equals little f. Yeah? So it means that the derivative of g prime and f prime are the same. And we've done these kind of exercises before, right? All this kind of stuff before. So if we imagine this function f and this function g, and their slope at each point is the same, then if the slope is the same, then whatever f is doing, if we do underneath it some function which has the same slope, we see there's a very tight relationship between f and g, right? In fact, f and g have to differ by at most a constant. That's what we see from the consequences of having that information when we draw the pictures. Yeah? And indeed, just from some use of the math, use of the language, if we differentiate f minus g, this is f prime minus g prime, which is just equal to 0 because they're the same thing, right? So we have that this function f minus g has got derivative 0. And we learned from the mean value theorem that whenever we have a function which has got derivative 0, then that thing has to be constant, right? Because if it wasn't constant, then there would be a little point where one point it's higher or lower than it is at another point, and therefore the secant line connecting these 2 points would have a slope, and therefore by the mean value theorem there is some point in between those 2 points where the derivative has got the same slope as the secant line, right? And that's impossible, yeah, because the derivative is 0. Therefore, the only way a function can have 0 derivative is if it's completely flat, right? We've learned this already. Yeah? So this has to imply that f minus g is constant, and let's see, but I mean g is constant, i.e. f equals g plus constant c. All that is a more mathematically complete explanation for this picture right here. Yeah? So we knew that that had to be the case from our picture. Now we've expressed our thoughts more carefully in the language of math. Huh? Cool. So that's a true fact. It's a fact we essentially already knew. We're going to use that fact the following way. So this is the fundamental theorem of calculus in all of its glory. So suppose f is continuous on the interval AB. Yeah? And capital F is an antiderivative. As we know, there are many antiderivatives. Then this definite integral from a to b of f is just what happens when we take the antiderivative capital F, take f of b minus f of a. Okay, so that means to explicitly find the antiderivative, we just need to find the to explicitly find the definite integral, we just need to find the antiderivative. So let's put over here some consequences. So recall, antiderivative of x squared is x to the 3 over 3 plus constant c, right? So if we want to integrate from 0 to 1, x squared dx, we just put that one of those antiderivatives, let's just take the one where there's no constant, and we put f of 1, which will just be a third, minus f of 0, which will be 0, which is a third. And then we have the area under the graph of x squared from 0 to 1, which is a third, which we know already because we worked to do that, but we had to work hard to get this, right? We had to do the Riemann sum. We had to have this explicit formula for the sum of I squared from I equals 1 up to n. We had to take the limit. This was not an easy thing to do, yeah? But we were able to do it. Okay, let's do another quick example. So anti-d of x to the 3 is x to the 4 over 4 plus constant c. Okay, and if we consider the integral from 0 to 3 of x to the 3 dx, by the theorem over there, we take one of the antiderivatives. Let's just take x to the 4 over 4, and then we put in the endpoint 3. So we're going to have 3 to the 4 over 4, and then the endpoint 0, which would just give us 0. So it's just going to be this. So that's the same as 9 squared over 4, which is 81 over 4, which is something else that we worked out, right? But again, with great effort. We worked this out in the last video class. And this took us a while. We had to have this explicit formula for the sum I equals 1 up to n I to the power 3. And that wasn't easy, right? But now it's seconds. We can do it in seconds. Yeah, we can recover the answer in seconds with this thing here. This is an incredibly powerful theorem. This renders all of our hard work unnecessary. We can just do this by coming up with the antiderivative. For these functions, these polynomial type functions, finding the antiderivative is trivial, right? So this is an absolute game changer. This transforms the problem of finding the definite integral of some function into a much easier problem of simply finding the antiderivative. We already know how to find many antiderivatives. Yeah? So let's see why this is true. Okay. This is the big theorem. And why? Well, we know g of x, which is defined to be a to x f of t, the increasing area function, is an antiderivative. Okay. And then by definition of g, this definite integral, a to b, f of x dx, is just what happens when we do g of b, right? If we stick in b into this, we get exactly this expression. Yeah? And that's also the same as g of b minus g of a, because g of a is the integral from a to a. That has got zero area, right? There's no area underneath the graph of a function from a to a, right? So that is the same as that. And we also know that g of x is equal to f of x plus some constant c, because this is what we just discussed right here. If we have two antiderivatives of the same function, they differ by a constant. So if f, capital F, is an antiderivative, then at most it's different from g by some constant, right? So g is equal to capital F plus some constant c, right? So putting it into this, let's call this thing star. We have that the integral from a to b, f of x, x, and we're going to replace g by f of b plus constant c minus f of a plus constant c. Constants cancel, and this is just f of b minus f of a. And that's it. That's exactly the theorem, right? That's exactly what we promised. So we can have any antiderivative, any one at all, and it remains true that the integral from a to b of little f is just what happens when we plug in the endpoints into the antiderivative f of b minus f of a. Huh? Cool, just as we saw there. So actually the heart of this is the fact that this function g is the increasing area function. This guy is an antiderivative. So part one actually is the thing that makes this work, right? And part one just was, again, this picture. We just created this picture, right? That's all we did. Here is x plus h, and all we did was consider the area of this strip, because the area of this strip is g of x plus h minus g of x. Yeah? So g of x plus h minus g of x over h is the height of the strip, right? Well, this is the graph of f. Which is approximately equal to f of x. And as h goes to 0, it's more and more like f of x. In other words, in the limit, it is f of x, and that's it. Yeah? So this picture is the heart of it. This is the heart of it. Okay? This is the heart of our theorem. And this is an absolute game changer. As I said, this changed everything. Because pre-Newton and Leibniz, there were people like me talking in front of people like you, students learning their math, And the very best, very most knowledgeable, the smartest math professors in the world were working out the definite integral of specific functions by doing the Riemann sum type stuff that we were doing, working very hard for each individual function, needing a different formula for each function, right? It was a serious research topic to actually find the area underneath the graph of specific functions. People would work for a long time, for years, to try and do that for specific functions for which that wasn't known. It's a difficult question, yeah? And then came along this very simple, very geometrical idea that once you see it, it's amazing that you haven't seen it before. But once you see it, once you see that this is the case, that we can create some antiderivative g in this way, and once we have this, and the fact that any two antiderivatives just differ by a constant, then we can just evaluate all of these definite integrals by just knowing the antiderivatives and plugging in f of b minus f of a. That just changes everything. We would not be able to explicitly calculate all the definite integrals that we want to calculate, that we need to calculate to bring civilization from the 17th century to the 20th century. We would not be able to do that without this tool. We would not have had an industrial technological revolution. We would have maintained a 17th century existence. We would be an agricultural society with an economy that functioned by trading agricultural goods and a few other manufactured goods manufactured in tiny workshops by hand, transported across canals, pulled by horses. We would be living that kind of life, were it not for this ability to explicitly calculate integrals that this gives. For many practical problems, to build your steam engine so it doesn't explode, to build all the stuff that you actually need to transform society into what we have now, you need to be able to do this, to explicitly calculate definite integrals. This is the fifth algebraic, the fifth operation after addition, multiplication, subtraction, and did I say them all? Addition, subtraction, multiplication, and division. The fifth is integration, this generalized form of addition. And it's one that we need. We need to be able to explicitly integrate things. And we can do it with this. So this is one of the high points of your entire degree. Seeing this theorem, seeing why it's true and seeing why it's important. This is one of the best ideas humanity's ever had. And and its consequences are profound. I mean, I do areas of research that are the kind of outgrowth of calculus, and this is used all the time. This is implicit all the time. This is absolutely used. I must use this like 1,000 times a day, or maybe not 1,000. Maybe I use this 100 times a day in one form or the other. It's so basic, it's so fundamental. So. Yeah, I want you to understand this, and I really want you to be clear as to why this picture gives this true fact. And and if you do, then this, of course, makes sense. This isn't a mystery. It's not magic. It's just pictures. As always, it's just pictures. Okay, cool. With this super strong theorem, we can now not only do simple things like this, we can do a lot of other questions that otherwise would be extremely hard for us. So here's some basic examples. We can do this. So the antiderivative of e to the x is e to the x, right? So this is just e to the 3 minus e to the 1, and that's it, right? So here's some notation. We are going to write things like this. This will mean f of b minus f of a. Yeah? Let's do another example. Let's do 3 to 6. The antiderivative of this thing is log, right? So then this thing will just be which is log of 6 minus log of 3, which is just log of 6 over 3, which is log 2. And imagine trying to do those things without the fundamental theorem of calculus, trying to do them with Riemann sums. That would be quite a work, right? That would be quite a difficult task. Okay, let us end with a final thing. If we do something like this, so example, the integral from -1 to 3, 1 over x squared. Okay, so the antiderivative of 1 over x squared is -1 over x, right? If we differentiate -1 over x, we get this thing. Yeah? And if we try and evaluate 3 to the -1 of -1 over x, like this, let's pull out the -1, and then that's going to be 1 over 3 minus 1 over -1, which is going to be -4 over 3, right? Because this minus becomes plus, so it's just a third plus 1, -4 over 3. But do we believe that this is a definite area of this quantity? Is -4 over 3 definite area of 1 over x squared from -1 to 3? Hopefully you don't believe it, because if we draw a picture and try and visualize what this thing looks like, we know that 1 over x squared blows up at 0, right? So it looks like this, right? It looks like this, like this. This is what it looks like from -1 to 3. So this is definitely a positive quantity, because it's always above the x-axis. So how can it be that we just did this and we conclude that it's -4 over 3? So what would be really good would be for you to stop the video and just think about it. What just happened there? Why am I getting this nonsensical answer? So pause, think about it, think hard, and then when you have an answer, or when you're sure you can't come up with an answer, press play again. Okay, so what's going on? Well, this is indeed correct that the antiderivative of 1 over x squared is -1 over x. That's true, for sure. And we have done this little algebraic, whatever, calculation correct. What isn't correct is that we can apply the fundamental theorem of calculus to this function, because this function is not continuous over this interval from -1 to 3, right? So you look at this picture here. The reason we can do this is that the graph of f is continuous, so that when we create some little slice like this, when at h goes to 0, then we get a meaningful quantity, right? If we had a vertical asymptote occurring right there, then we wouldn't have a meaningful quantity, because we wouldn't be able to say the limit is equal to f of x. It just wouldn't be true. It just wouldn't make sense, right? So we can only do stuff like this if this thing is actually continuous at every point from A to B. Without that fact, then this just isn't true. It's just not a true fact, right? If we had a jump discontinuity like this, right? And then what would we have? We'd have something that doesn't give us the answer that it's meaningful. We just don't have the same thing as true. It's not the case that the set of everything underneath the graph from x to x plus h is going to tend to f of x or close to f of x if there's a jump discontinuity up here, right? It'll just be false. So we can't apply this theorem. So what is seductive about this theorem is that it's so easy to apply. These are easy things to do, right? These are very quick calculations, and they quickly give the answer. So it's very tempting to just start to apply them like a robot, just to see something, go, okay, I know the antiderivative, I've got it, I'm plugging in the endpoints, that's the answer. Yeah? And you can get obviously completely false results from doing that. So as I emphasize, we are going to try and avoid just performing algorithms without thinking about what we're calculating, what the thing means. And if you have that deeply enough embedded as a habit, then hopefully, even if you did do this, you'd look at this minus 4 over 3, and then you'd think, what does this function 1 over x squared look like? And go, okay, it's a positive function, something is wrong. And then hopefully you backtrack and you realize, okay, looking at this even closer, I realize it's horribly discontinuous at 0, therefore I can't apply the fundamental theorem of calculus. So you would find your error if you are sufficiently visualizing, engaged with the meaning of this stuff, right? If you are doing the stuff that I'm emphasizing, you would be saved from making this error, even if you are doing this in a hurry and the time pressure. If you don't, if you just are memorizing algorithms, then, and not thinking about what any of this stuff means, then this seems perfectly reasonable. And indeed, we try and test with this kind of stuff plenty of times, and lots of people fall for it, and it's easy to do. And perhaps when I asked you to pause and try and find what's wrong with it, you couldn't find what was wrong with it, right? But now, after I've shown it to you, you do. So please keep this in mind as a kind of salutary lesson that, powerful though this is, it's only meaningful when we have the conditions where we can apply it. And even if you can get an answer out rather quickly, rather easily, doesn't necessarily mean it's the correct answer unless you have the conditions where you can apply it. Yeah? So don't switch off your brain and just start to do this as an algorithm, one after the other. Think about what you're calculating. Think about if the answer you get is meaningful before you're satisfied with the answer that you obtain. Yeah? This is a powerful tool, but only if you use it where it can be used. Otherwise, it'll take you astray. Okay, that's it for today. Have a great day. I will see the Wednesday group on Wednesday.